This course is designed to give you an understanding of the basic concept of manipulating force through a hydraulic system using pressure control valves. The two basic design types of these valves are direct acting and pilot operated.
The primary concern in fluid power circuits is to either control the rate of flow or the pressure level. One misconception has been that pressure may be controlled with an orifice or flow control device. This is never accomplished with any degree of accuracy. For accurate control of force, 6 types of pressure controls have been developed. They are relief valve, unloading valve, sequence valve, reducing valve, counterbalance valve, and brake valve. By symbol, these valves closely resemble one another. Often, only their location in the hydraulic circuit will designate what type of pressure valve they are. Maximum system pressure can be controlled with the use of a normally closed pressure valve. With the primary port of the valve connected to a system pressure and the secondary port connected to tank, the poppet is actuated by a predetermined pressure level, at which point primary and secondary passages are connected and flow is diverted to the tank. This type of pressure control is known as a relief valve. A direct-acting relief valve is one in which the poppet is held closed by direct force of a mechanical spring, which is usually adjustable. Spring tension is set on the knob to keep the poppet closed until system pressure working against the poppet reaches the desired cracking pressure. When the system pressure reaches full relief value, all fluid is passed across the poppet to the tank passage. It should be noted that direct-acting relief valves are usually available in only relatively small sizes because it is difficult to design a strong enough spring to keep the poppet closed at high pressure and high flow. Pilot-operated relief valves are designed to accommodate higher pressures with higher flows being confined to smaller frame size than a direct-acting relief valve with the same rated flow capacity. The valve is built in 2 stages. The second stage includes the main spool, held in a normally closed position by a light, non-adjustable spring. The second stage is large enough to handle the maximum flow rating of the valve. The first stage is a small direct-acting relief valve, usually mounted as a crosshead on the main valve body, and includes a poppet, spring, and adjustable knob. The second stage handles full rated flow to the tank. The first stage controls and limits pilot pressure level in the main chamber. Relieving action through the main spool is as follows. As long as the system pressure is less than relieving pressure set on the control knob, pressure in the main spring chamber is the same as pump line pressure because there is no flow through the control orifice, and consequently there is no pressure drop from one side of the orifice to the other. When pump line pressure rises higher than the adjustment set on the control knob, the pilot relief poppet moves off its seat. This starts oil flow from the pump line through the orifice, across the pilot relief poppet, and to the tank. This restricted flow caused by the orifice creates a pressure difference between the pump line and the area across the pilot orifice. This pressure imbalance causes the main poppet to move off its seat. This will discharge enough of the pump flow to prevent any further rise in the pump line pressure. When pump line pressure drops below the control knob setting, the pilot relief closes, flow through the orifice ceases, and the main spring can reseat the main poppet. The pilot-operated pressure relief valve comprises a valve body, a main spool cartridge, and a pilot valve with a pressure setting adjustment. The pressure present in the primary port acts on the bottom of the main spool, and at the same time the pressure is fed to the spring-loaded side of the main spool via the control lines and containing orifices. The pressure is also present at the ball of the pilot valve. If the pressure increases to a level above the spring setting of the pilot valve, the ball opens against the spring. The pilot oil on the spring side of the main spool cartridge now flows into the spring chamber of the pilot valve and is directed internally to the secondary port and back to the tank. Due to the orifices in the control line between the primary port and the pilot valve, a pressure drop or pressure differential exists between the bottom of the main spool and the spring side of the main spool. This pressure differential lifts the main spool off its seat and connects the primary pressure port of the valve to the secondary or tank port. Fluid now flows to the tank, maintaining the set operating pressure of the valve. A sequence valve is a normally closed pressure control valve that ensures that one operation will occur before another based on pressure. In our clamp and drill system, we want the clamp cylinder to extend completely before the drill cylinder extends. To accomplish this, we place a sequence valve just before the drill cylinder. We set the valve to 500 psi. This will ensure that the drill will not extend before we have reached 500 psi on the clamp cylinder. Notice that once the drill cylinder has extended, pressure will continue to rise to the system relief setting of 1500 psi. A pressure-reducing valve is a normally open pressure control valve used to limit pressure in one or more legs of a hydraulic circuit. Reduced pressure results in a reduced force being generated. A pressure-reducing valve is the only pressure control valve that is normally open. A normally open pressure control valve has primary and secondary passages connected. Pressure at the bottom of the spool is sensed from the pilot line, which is connected to the secondary port. Remember, a pressure-reducing valve is normally open. Now, let's place our pressure-reducing valve in an actual circuit to see its application. The illustrated clamp circuit requires that clamp cylinder B apply a lesser force than clamp cylinder A. A pressure-reducing valve placed just before the clamp cylinder B will allow flow to go to the cylinder until pressure reaches the setting of the valve. At this point, the valve begins to close off, limiting any further buildup of pressure. As fluid bleeds to the tank through the valve drain passage, pressure will begin to decay off and the valve will again open. The result is a reduced modulated pressure equal to the setting of the valve. A counterbalance valve is a normally closed pressure valve used with cylinders to counter a weight or potentially overrunning load. In this circuit, without a counterbalance valve, the load would fall uncontrolled or overrun, and pump flow would not be able to keep up. To avoid the uncontrolled operation, we place a counterbalance valve just after the cylinder. The pressure setting of the counterbalance valve is set slightly above the load-induced pressure of 1000 psi. This counters the load. As we extend the cylinder, pressure must slightly rise to drive the load down. Now that you understand the application of a counterbalance valve, push the extend and retract buttons to watch the function of the valve. A brake valve is a normally closed pressure control valve with both direct and remote pilots connected simultaneously for its operation. This valve is frequently used with hydraulic motors for dynamic braking. Because any downstream resistance will add to the load on the hydraulic motor, we pilot remotely using working pressure to keep the valve open during running. This eliminates back pressure on the motor. When we de-energize the directional valve, remote pilot pressure is lost, allowing the valve to close. The inertia of the load will now drive the valve open via the internal pilot, giving us dynamic braking. Now that you understand the application of a brake valve, push Energize, then stop to see the valve function.
An unloading valve is a remotely piloted, normally closed pressure control valve that directs flow to the tank when the pressure at that location reaches a predetermined level. A high-low system is a good example of an unloading valve application. This system may consist of two pumps, one being a high-volume pump and the other being a low-volume pump. As the cylinder approaches the load, the pressure requirement is low. If the pressure requirement is below the unloading valve setting, both pumps work together to provide a rapid approach to the load. At this point, the system pressure increases, thereby opening the unloading valve. The flow from the high-volume pump is directed back to the tank at a minimal pressure. The low-volume pump continues to deliver flow for the higher pressure requirement of the work cycle. Once the flow from the high-volume pump is unloaded, both pumps join once again for a rapid return of the cylinder. The high-low system requires less input power to meet the work cycle's speed and force requirements. Now that you understand the application of the unloading valve, push the extend or the retract button to watch the function of the valve.
The directional control valve is the component that starts, stops, and changes the direction of fluid flowing through a hydraulic system. In addition to this, the directional control valve actually designates the type of hydraulic system design, either open or closed. This course will give you a hands-on opportunity to see how these valves actually operate and the importance that they play in proper system function.
Directional control valves are used to start, stop, and change the direction of flow in a hydraulic circuit. Although they may be designed as rotary or poppet style, the spool-type directional control is the most common. This design consists of a body with internal passages that are connected or sealed by a sliding spool along the land of the valve. Directional spool valves are sealed along the clearance between the moving spool land and the housing. The degree of sealing depends on the clearance, the viscosity of the fluid, and the pressure. Because of this slight leakage, spool-type directional valves can not alone hydraulically lock the actuator. Directional control valves are primarily designated by their number of possible positions, port connections or ways, and how they are actuated or energized. For example, the number of porting connections are designated as ways or possible flow paths. A four-way valve would have 4 ports, P, T, A, and B. A 3-position valve is indicated by 3 connected boxes. There are many ways of actuating or shifting the valve. They are push button, hand lever, foot pedal, mechanical, hydraulic pilot, air pilot, solenoid, and spring. Directional control valves may also be designated as normally open or normally closed. These designations would accompany 2-position valves such as the following: spring offset, solenoid operated, 2-way valve, normally closed. Spring offset, solenoid operated, 2-way valve, normally open. Spring offset, solenoid operated, 3-way valve, normally closed. Spring offset, solenoid operated, 3-way valve, normally open. The spool-type directional control valves in industrial applications are subplate or manifold mounted. The porting system is industry standard and designed by valve size. Directional control valve sizing is according to flow capacity, which is critical to the proper function of the valve. Flow capacity of a valve is determined by the port sizes and the pressure drop across the valve. This mounting pattern and size is designated as a DO2 nominal flow 5 gallon per minute, DO3 nominal flow 10 gallon per minute, DO5 nominal flow 20 gallon per minute, DO5H nominal flow 25 gallon per minute, DO7 nominal flow 30 gallon per minute, DO8 nominal flow 60 gallon per minute, D10 nominal flow 100 gallon per minute. A direct-acting directional control valve may be either manual or solenoid actuated. Direct acting indicates that some method of force is applied directly to the spool, causing the spool to shift. In our illustration, energizing the solenoid or coil creates an electromagnetic force, which wants to pull the armature into the magnetic field. As this occurs, the connected push pin moves the spool in the same direction, while compressing the return spring. As the spool valve shifts, port P opens to port A, and port B opens to port T or tank. This allows the cylinder to extend. When the coil is de-energized, the return springs move the spool back to its center position. Watch the whole animation uninterrupted. For control of systems requiring high flows, usually over 35 gallons per minute, pilot-operated directional control valves must be used due to the higher force required to shift the spool. The top valve, called the pilot valve, is used to hydraulically shift the bottom valve or the main valve. To accomplish this, oil is directed from either an internal or an external source to the pilot valve. When we energize the pilot valve, oil is directed to one side of the main spool. This will shift the spool, opening our pressure port to the work port and directing return fluid back to the tank. It is often required to externally pilot or send fluid to the pilot valve from an external source. The advantages to external piloting are constant pressure supply regardless of other influences in the main system, and the source may be filtered separately to prevent silting of the pilot valve. In addition to externally piloting, we may also externally or internally drain the valve. If the pilot valve is internally drained, oil flows directly into the tank port of the main valve. Pressure or flow surges occurring in the tank port when operating the main control spool may affect the unloaded side of the main spool, as well as the pilot valve. To avoid this, we may externally drain the pilot valve by feeding pilot oil flow back to the tank. Pilot-operated directional control valves may be field changed from internal to external pilot and drain. We can categorize most hydraulic circuits into two basic types, open center or closed center. The directional control valve actually designates the type of circuit. Open center circuits are defined as circuits which route pump flow back to the reservoir through the directional control valve during neutral or dwell time. This type of circuit typically uses a fixed volume pump, such as a gear pump. If flow were to be blocked in neutral or when the directional control valve is centered, it would force flow over the relief valve. This could possibly create an excessive amount of heat and would be an incorrect design. A closed center circuit blocks pump flow at the directional control valve, in neutral or when centered. We must utilize a pressure-compensated pump such as a piston pump, which will de-stroke. A three-position directional control valve incorporates a neutral or center position, which designates the circuit as open or closed, depending on the interconnection of the P and T ports, and designates the type of work application depending on the configuration of the A and B ports. The four most common types of three-position valves are open type, closed type, float type, and tandem type. This open type configuration connects P, T, A, and B together, giving us an open center and work ports that drain to the tank. This configuration is often used in motor circuits to allow freewheeling in neutral. This closed type configuration blocks P, T, A, and B in neutral, giving us a closed center. This center type is common in parallel circuits where we want to stop and hold a load in mid-cycle. This float type configuration blocks P while interconnecting A and B ports to T. Because P is blocked, the circuit becomes closed center. This center type is commonly used in parallel circuits where we are freewheeling a hydraulic motor in neutral. This tandem type configuration connects P to T while blocking work ports A and B. With P and T connected,
We have an open center circuit. This center type is used in connection with a fixed displacement pump. Because A and B are blocked, the load can be held in neutral. When specifying a directional control valve type, one must consider the type of circuit required and the work application.
In an open circuit, hydraulic fluid supplied to the pump inlet comes from the reservoir and is returned from the actuator back to the reservoir. In most open circuits, hydraulic fluid is fed to the actuator by a directional control valve and returned to the reservoir in the same way. This first circuit is a basic system with a hydraulic pump and a hydraulic motor. When the pump is in operation, flow is directed to the hydraulic motor, causing the motor to rotate. If the pump is not rotating, the hydraulic motor will not turn. In this circuit, a directional control valve is added to the circuit, and a bidirectional hydraulic motor replaces the hydraulic motor. The directional control valve will allow the hydraulic motor to reverse direction when shifted. This circuit adds an adjustable flow control valve and a pressure relief valve. The flow control valve allows for variable output speeds from the hydraulic motor. The pressure relief valve protects the system from overpressurization and will shift as the system pressure increases due to flow restriction in the flow control valve. In this circuit, a variable pump has replaced the fixed pump. The flow control valve is removed, an open center directional control valve is added, and a filter and heat exchanger are added to the return line. The directional control valve allows for forward or reverse direction of the motor and freewheeling of the hydraulic motor when the valve is centered. The filter and heat exchanger will condition the fluid before it returns to the reservoir. The variable pump will now allow for variable output speeds from the hydraulic motor. If the hydraulic motor rotation is restricted or stopped, the high pressure relief valve opens, protecting the system from overpressurization. A closed circuit normally means the hydraulic fluid is returned from the prime mover directly back to the inlet of the pump. In most closed circuits, the continuous leakage from the pump and motor is replenished by an auxiliary pump. This first circuit is a basic system with a bidirectional variable displacement piston pump and a bidirectional hydraulic motor. When the pump is on, stroke flow is directed to the hydraulic motor, giving it rotation. Rotation of the hydraulic motor is reversed when the piston pump swash plate goes over center. Controlling the output speed from the hydraulic motor is achieved by varying the output flow from the variable piston pump. If the pump is not rotating or is off stroke, the hydraulic motor will not turn. In this circuit, two pressure relief valves are added to protect the system from overpressurization. When the hydraulic motor rotation is restricted or stopped, the high pressure relief valve opens and protects the system from overpressurization. This circuit adds a small tank to hold the leakage from the pump and hydraulic motor. This leakage must be replenished to the closed circuit. In the last circuit, a fixed pump is added with a filter in the suction line, two spring check valves, and a charge pressure relief valve are added, and a heat exchanger is added to the leakage line from the pump and hydraulic motor. The fixed pump replenishes the hydraulic fluid that is lost from internal leakage from the pump and motor through the spring check valve into the low boost pressure line. The other check valve keeps the high system pressure isolated from the low boost pressure. When the auxiliary pump has replenished the low boost side, pressure builds slightly, opening the charge pressure relief valve. The charge pressure relief valve opens and fluid is directed back to the tank. The charge pressure relief valve maintains a constant pressure in the low boost pressure line, which charges the pump. When the hydraulic motor rotation is restricted or stopped, the high pressure relief valve opens and protects the system from overpressurization.
Flow control valves are used to regulate the volume of oil supplied to different areas of hydraulic systems. In this course, you will be given an overview of the two types of flow control valves, as well as their application and location in a hydraulic system. This course is provided to help you learn why and where flow control devices should be used.
The function of the flow control valve is to reduce the rate of flow in its leg of the circuit. Flow reduction will result in speed reduction at the actuator. A flow control valve builds added resistance to the circuit, increasing pressure, resulting in a partial bypassing of fluid over the relief valve, or a de-stroking pressure of a compensated pump. This reduces flow downstream of the flow control valve. This circuit uses a fixed volume pump. To reduce flow to the actuator, we must bypass a portion of the fluid over the relief valve. As we close the needle valve, pressure increases upstream. As we approach 1500 psi, the relief valve begins to open, bypassing a portion of fluid to the reservoir. When flow control is used in a pressure-compensated pump, fluid is not pushed over the relief valve. As pressure approaches the compensator setting of 1500 psi, the pump will begin to de-stroke, reducing output flow. Flow control valves may be fixed, or non-adjustable, or adjustable. In addition, they may also be classified as throttling only or pressure compensated. The amount of flow through an orifice will remain constant as long as the pressure differential across the orifice does not change. When the pressure differential changes, the flow changes. Change in load or upstream pressure will change the pressure drop across the valve. Meter in is the method of placing a flow control valve in such a way that fluid is restricted to the actuator. In this circuit, without a flow control valve, the cylinder extends and retracts at an unrestricted rate. When we place a flow control valve into the circuit, this flow control valve will restrict flow to the cylinder, slowing the extend rate of the cylinder. The check valve allows return flow to bypass the flow control when direction of flow is reversed. When we move the flow control to the other line, the cylinder extends at an unrestricted rate. We can restrict the flow to the cylinder so that it will retract at a reduced rate. The advantage to meter in is that it is very accurate with a positive load. However, when the load goes over center, the load becomes negative or overrunning. The load is no longer being controlled by the cylinder. As the load overruns, it causes the cylinder to cavitate. Although meter in is usually the best placement for controlling a constant speed because it also dampens flow and pressure transients, it may be required in some applications to meter out. To meter out, we simply change the direction that the flow is allowed to pass through the reverse check. This will cause the fluid to be metered as it leaves the actuator, which is opposite of meter in. In this
Finally, we'll close our work in this section with an overview of modular valves. You may already be familiar with modular valves, including cartridge and stack valves. In this section, you'll learn the hows and whys of modular valves to enhance system design and troubleshooting. For example, you'll see how these valves help designers eliminate many of the problems associated with external plumbing between valves, and you'll increase your expertise in the operating principles and use of these valves.
Stack valves are bolted together in a compact stack, eliminating the need for external plumbing between components. By eliminating the pipes, tubes, and hoses typically used to interconnect the various valve components, the assembly is compact and The directional control valve is always located on the top of the stack. The relief valve should be placed at the bottom of the stack next to the subplate. Flow control valves and pressure control valves are placed between the relief valve and the directional control valve. Using proper procedures when assembling stack valves will produce a leak-free circuit. Clean and check all O-ring seats for damage. Center new O-rings in each seat, and alternately tighten the mounting bolts until all bolts are properly torqued. A single valve stack can be mounted on a manifold block or subplate, while multiple valve stacks can only be mounted on a manifold block. Each valve stack would be used to control an actuator. Stack valves can be mounted on a manifold block in conjunction with circuits containing cartridge valves. Subplates and manifolds have a supply P port, a return T port, and A and B work ports, which line up with corresponding P, T, A, and B ports on the mounting surface. Manifolds and subplates with X and Y ports can be supplied when using directional control valves that require an external pilot or external drain. Watch as the following components are converted to a schematic of a single stack that controls an actuator. The relief valve is placed next to the manifold to provide protection to the circuit. Pressure and flow controls are sandwiched in between the relief valve and the directional control valve. The directional control valve, which only has one mounting surface, is always at the top of the valve stack. This schematic represents a system of 3 valve stacks mounted to a 4-station manifold. The alternating dot and dash lines are enclosure lines. Each component outlined by an enclosure line represents a module with its internal passages. A blanking plate is used to block the ports of the unused station. There are 4 flow paths through each valve stack. The pressure and return passages through the stack assembly connect the pressure and return ports of the directional control valve to the respective ports on the manifold. The A and B work passages through the stack assembly connect the work ports of the directional control valve to the ports of the actuator. The system relief valve is located in the stack closest to the common supply and return ports. Stack valves are available in 4 ISO sizes. The ISO size 02 valve has a maximum pressure rating of 215 bar and a flow rating of 30 liters per minute. The ISO size 07 cartridge valves can be used to perform flow control, pressure control, and directional control, load holding, and logic functions. They are a very compact design that must be installed into special cavities in valve blocks or manifolds. Cartridge valves, used in combination with a manifold, can be used to create a common circuit free of potential leaks associated with external plumbing. Cartridge valves can be divided into 2 design categories, screw-in and slip-in. The screw-in style cartridge valve uses a threaded base to secure the valve in the cavity. Screw-in cartridges use either a spool, poppet, or ball valve element. The spool element can be used for 2-way, 3-way, or 4-way flow functions, while the poppet and ball elements provide for only a 2-way flow function. Screw-in cartridge valves are typically used in low-flow systems where the flow is 35 gallons per minute or less. Some of the available screw-in valve configurations are check valve, relief valve, needle valve, solenoid-operated directional control valve, and manually operated directional control valves. Slip-in cartridge valves are used for large flows, over 30 gallons per minute. They are similar in design to poppet-style check valves and are made to slip into standardized cavities in a manifold block. A control cover is bolted on top to secure them in the cavity. The control cover has passages for pilot flow to operate the valve insert, which you can consider as the main stage in a two-stage valve. The slip-in cartridge element is controlled by a directional control that is bolted to the control cover. By using 4 slip-in cartridge valves with a directional control on each to operate a cylinder, you will get 12 flow path combinations. Because you can use individual slip-in cartridge valves for each flow path, you can select sizes that are appropriate for the amount of flow. For example, the flow out of the rod end of a cylinder is less than from the cap end due to the similar volume in the rod end. A conventional valve would have to be sized for the larger flow from the cap end, while the individual cartridges allow you to use smaller sizes for smaller flows. The result is more compact, economical valving. Slip-in cartridges are available in several area ratios. The area ratios and the pressure at each port determine whether the valve will open or close. The following are features represented on a slip-in cartridge valve symbol. The area ratio given by the relative widths of the parts of the poppet. For example, the 1-to-1 ratio shows that the top and bottom of the poppet are the same width, while the 1-to-2 ratio shows that the top is twice as wide as the bottom. If the valve is used to control flow, it will use a triangle to indicate a throttle notch in the poppet. The closing spring is part of any slip-in cartridge valve. The supply and working ports are indicated by A and B. The pilot port is indicated by A sub P.
Manifold blocks should be thoroughly cleaned before installing cartridge valves. New manifold blocks may have metal chips and other contaminants left in the cavities and passages from the machining process. Prior to assembling, the manifold block should be flushed repeatedly. Next, compressed air should be blown through all ports and passages, and each opening wiped clean with a lint-free rag.